today we have 5 different topics we're going to cover, and I'll go through them one at a time, cover as many points as I can in the time that we have. The first, I'd like to review with you word numbers in scientific notation. Now, a number like 4.0 times 10 to the 5th, if multiplied by another number in scientific notation, let's say 2.0 times 10 to the 3rd, can best be manipulated by separating out the non-exponential part from the exponential part and doing them separately, as I think I've mentioned in class. So we would multiply the 4 times the 2, giving us 8.0, and multiply 10 to the 5th times 10 to the 3rd. And this is the part that I want to review with you especially. When we multiply 2 powers, we add the exponents together. Can you remember that? So the result here will be times 10 to the 5 plus 3 is 8. Okay? Now, what if we had negative exponents? Do an example of that. 4.0 times 10 to the minus 5th times 2.0 times 10 to the minus 3rd. We're adding negative numbers, but the principle is exactly the same. Okay? So once again, 4 times 2 is 8. And we add minus 5 plus minus 3, and we get minus 8. Okay? Times 10 to the minus 8. What if we mix them? We have 4.0 times 10 to the minus 8 times 2.0 times 10 to the plus 3. Well, once again, we simply add them together. So the result will be 8.0 times 10 to the, what do you suppose? 10 to the 5th. Minus, not 10 to the minus 5th. Minus 8 plus 3 is minus 5. Right? Okay. Let's do some division. This time, we'll divide 4.0 times 10 to the 5th by 2.0 times 10 cubed. Once again, we do this part separate from this part. This quotient is 2.0, and this quotient, instead of adding the exponents together when we're dividing, we subtract the exponent in the denominator from the exponent in the numerator. And so we get 10 to the 5 minus 3 is 10 squared. Let's do an example with negative exponents. We'll do 5.0 times 10 to the minus 5th over 2.5 times 10 to the minus 3. This is 2. And what's this? Well, minus 5 minus minus 3 is the same as minus 5 plus 3. Right? Minus 5 plus 3 is minus 2. That would be times 10 to the minus 2. And why don't we try mixing them this time? We'll do 6.0 times 10 to the minus 5. No, let me do plus 5 on the top over 2.0 times 10 to the minus 3. Well, this is 3.0, and that will be times 5 minus minus 3 is the same as plus 3. So that will be times 10 to the 8th. Does that make sense? Okay. Now let's do adding and subtracting. Now for those of you for whom this is a review, bear with. Maybe sooner or later we'll get to something you don't already know. Okay. Let's do adding and subtracting. I want to add 4.0 times 10 squared to 2.0 times 10 cubed. The only way you can add and subtract numbers in scientific notation is to get both numbers to have the same exponent. All right? So we've got to convert either this to a power of 10 to the 3 or this to a power squared. We could do it either way. Why don't we convert this one to a power of 10 to the 3? If I want this to be not times 10 squared, but times 10 cubed, I'm going to have to move this over, right? So that's the same as 0.40 times 10 cubed plus 2.0 times 10 cubed. And I would add them the same way I would add any numbers. I'm going to put them in a column here. We draw a line here so we don't get messed up. 2.0 times 10 cubed. Now that these are exactly the same, I can simply add these two numbers together, and the result will be whatever that is times 10 cubed. We just keep the times 10 cubed all the way through. So this will be 2.40 times 10 cubed. Any questions so far? Yes, ma'am.
When you're adding them together, you're going to use the smallest place value, so it should be 2.4 instead of 2.40?
Yes, I think you're right. I like that. I like that comment. Very good. Thank you. Okay, are we tired of that? Let's go on to something else. Let's talk about logarithms. Those are fun. The question, if the logarithm of a number x is 5, or in other words, the log to the base 10 of x equals 5. And by the way, we're only going to deal with logs to the base 10 in this class. You may have learned about other kinds of logarithms, like natural logarithms, for example. Then what is the value of the number itself? What is x? Well, let's review for ourselves what a logarithm is. A logarithm is simply a different way of writing a number. A logarithm is the exponent to which, let's see, I better not put x up there. The exponent to which 10 has to be raised in order to give you the number of interest. You can express 5 as a power of 10, but that's a little odd. What's easier is to express 100 as a power of 10. What's 100 as a power of 10? It's 10 squared. It's 10 to the power of 2. What's 1,000? 10 to the power of 3. Well, you can express a number between 100 and 1,000 also as a power of 10. It won't be a nice whole number like 2 or 3. It'll be something, as a matter of fact. But the point is that you can express any number as a power of 10. Well, if the log of our number x is 5, that means that 5 is the exponent of 10, which gives you that number x. So x must be 10 to the 5th, which is what in everyday parlance? 5th is 100,000. Okay? So if the log of x is 5, then x is 100,000. Any questions about that? The next question was the log to the base 10 of 0.0010 is, well, let's see here. What are we really asking? We're asking what power would I have to raise 10 to give me that number? What power would I have to raise 10 to give me that number? What would that be? Well, it'd be a -3, right? If I had, let's see, I've moved over 3 decimal places, right, to get a good scientific notation number. So .001 is 10 to the minus 3, and the logarithm, therefore, is 3. Minus 3, sorry. Okay? Now, that means that this number is the same as 1/1000th. Isn't that true? 0.10th, 0.01 is 100th, 0.001 is 1,000th. It's the same as 10 to the minus 3. That means the logarithm of that number is minus 3. Yes?
That wouldn't be minus 4?
No, because, let's see, I'm not sure how to explain it, but as a matter of fact, that's how you count if you want to. You count over this 1, 2, 3. Okay. What is the logarithm of 1? It's 0, right? The logarithm of 1 is 0. What's the logarithm of 10? 1. What's the logarithm of 0.1? Negative 1. What's the logarithm of 0.01? Negative 2. What's the logarithm of 0.001? Negative 3. Am I making sense? Okay. Am I making sense for you?
Not yet.
Not yet.
I'll keep listening.
Okay. Now, if this is 0.0001, then the logarithm would be negative 4. 1, 2, 3, 4. Okay. Yes, back there.
When you're saying the logarithm of 1, 2.01, that's just assuming that that 10's there, and that's because we're not going any more depth than just having a 10 there on the logarithm, right?
I'm sorry, I don't understand your
logarithm-
question. Can you talk louder, please?
On the logarithm, we always just assume that that's to the 10th power, whatever.
Yes, you can have a logarithm to any base number.
But
We're only going to deal with logarithms to the base of 10. Okay? It's what power you have to raise 10 to give you that number. Okay? So let me just write it down for you in a sequence for those of you who are skeptical. All right? We'll start with 1. 1 is equivalent to 10 to the 0 power, you told me. So the logarithm of 1 is 0, right? What about 10? 10 is the equivalent of 10 to the 1. What's the logarithm of 10? 1. Okay? 100 is 10 squared. What's the logarithm of 100? 2. Now let's go backwards. 0.1, 1/10 is equal to 10 to the minus 1. What's the logarithm of 0.1? Logarithm of 0.1 is minus 1. Am I making, you see a pattern here? Okay, so 0.01 is 10 to the minus 2. The logarithm of 0.01 is minus 2. 0.001 is 10 to the minus 3. What's the logarithm of 0.001? Minus 3. Okay, questions? Yes, sir.
So with this, when it's negative, you can't just move the decimal like in scientific notation?
No, this is kind of different stuff here. Scientific notation is a little bit different. But do you see the pattern here and how that works? Are you convinced now?
I was convinced before, but
Oh, good.
I understand now.
Okay, good. Okay. The next question says, oh, this is an easy one now. This next question, you'll be able to get this one without any problem. It says the log of 10 to the minus 2.4 is what? The log to the base 10 of 10 to the minus 2.4 is what? Somebody tell me. It's minus 2.4. It is the power you have to raise 10 to give you the number of interest. Now, what is the number of interest? Turns out it's expressed as a power of 10 array. It's 10 to the minus 2.4. What power do you have to raise 10 to get 10 to the minus 2.4? minus 2.4. Is that clear? Any question about that? Okay. Would you raise your hand if it is clear to you, please? Thank you. That helps. Now, if this isn't clear, then it's important that you come and see me in office hours or talk to your peer mentor in office hours or go to the tutorial lab. Make sure this is clear because as time goes by, you're going to need this stuff. Okay, if the log, here's another one, if the log x equals 2.5, then what's the value of x? Could somebody help me out there? If the log is 2.5, then what is the value of x?
10 raised to the
Yes, right there. It is 10 to the 2.5. Now you might say, well, what is that? Well, let's think. Where would that fall in the range of numbers? You know that 10 to the 2, or 10 squared, is what? 100. You know that 10 to the 3 power is 1,000. So 10 to the 2.5 power is going to be somewhere in between 100 and 1,000. Make sense? Now, if you wanted to know exactly what it was, you could turn to your calculator, and your calculator would tell you exactly what that number would be. Does anybody have a calculator here? I'm curious what that number is. Okay, would you yell it out real loud?
316.2.
Okay, is there any way that you could have figured that out without a calculator? How would you figure it out without a calculator? I don't think I could, but maybe there are ways that you can do this in your head, but I wouldn't do that, right? But I would expect you to know this much, right? At least that much. And then you could use your calculator to figure out what the number actually was if you needed to. Okay, that's the questions that were on the quiz. Now, I wanted to talk about logarithms of numbers in scientific notation. So let's say we have a number like 1.0 times to the fifth. What's the log to the base 10 of that number? Well, that's the same as just 10 to the fifth, right? And so the logarithm is 5. Now what if it were 2.0 times 10 to the fifth? It turns out that if you have two numbers that are multiplying together, as you do in this case, the logarithm of the product is the sum of the logarithms of the individual parts. I'll say that again. If you have two numbers you're multiplying together, the logarithm of the product is the same as the sum of the logarithms of the individual parts. That's the same as the log of this whole number here is equal to the logarithm of 2.0 plus the logarithm of 10 to the fifth. Now, you probably don't know what the logarithm of 2.0 is. We could use our calculator. But you can tell me what the logarithm of 10 to the fifth is. What is it? 5. So it's some number plus 5. I wonder where this number would fall. Let's think. Let's just reason this through. Find numbers that are close by. What's the logarithm of 1? 0. Okay. What's the logarithm of 10? 1. 2 is somewhere between 0 and 10, isn't it? So the logarithm of 2 is going to be somewhere between 0 and 1. Right? So this is going to be some number between 0 and 1. Somebody tell me what the logarithm of 2 is. 0.3. Roughly. Okay, so 0.3 plus 5. So the logarithm is going to be 5.3. the same thing with a negative exponent this time. I'll just use the same example here, except I'll change that to a minus 5 for the exponent. Again, we can just add these together. It's the logarithm of 2 plus the logarithm of 10 to the minus 5 this time. What's the logarithm of 10 to the minus 5? Minus 5. Now you told me that the logarithm of 2 is 0.3. So the logarithm of this number is going to be minus 5 plus 0.3, which will be minus 4.7. Minus 5 plus 0.3 is minus 4.7. Right? Good, okay. Now I already told you that you can multiply numbers together by adding their logarithms. And that's true not just when you have times 10 to a power, but it's true for any two numbers. Let's say I want to multiply 2.3 times 5.6. I want to know what the logarithm of that product is. Well, that's the same as the logarithm of 2.3 plus the logarithm of 5.6. When I multiply numbers, I add their logs. What do you suppose happens when I divide numbers? Makes sense, doesn't it? So if we have the logarithm of 2.3 over 5.6, that's going to be the logarithm of 2.3 minus the logarithm of 5.6. Whatever those numbers have in, you could figure that out from your calculator. How are we doing for time? Okay. Okay. That was all I had planned to say about logarithms today. Are there any questions? Yes, sir.
So with logs, it's all based on 10, is that right?
In our class, now, not a mathematician could make a log out of any number. In our class, it will always be based on 10.
But, okay, you said it doesn't go above 10, but it won't be based on, it won't use any other number but 10.
No, as the base. I'm expressing, let's say I'm looking for the log of 2.3. I'm looking for the number here that 10 is raised to give me 2.3. I will always have a base of 10. But of course, be using any numbers. Any other questions? Yeah.
Is this all we're going to need to have to know about logs for this class, or is there more?
Well, it's all I could think of in advance. I mean, as we get to the position where we talk about pHs, which is where you need to use logs, other things may come up, but this is all I could think of for the moment.
Okay,
Okay? And maybe that's enough for now.
that works.
Okay, let's go on and talk about fractions. And to introduce this topic, I will refer back again to the quiz that we put on Blackboard. First question was, what is A over 1/3 equivalent to? Now, it turns out that if you have a fraction on the bottom of another fraction, you can simply flip the fraction on the bottom over and multiply. So that's the same as A times 3 over 1. It was over 1 over 3, it's the same as being times 3 over 1. Get the idea? So the answer here is 3A. Now A could be anything. This is dealing with fractions and variables when you're making calculations using equations. What if it were, let's see, A over 1/3 B? What would the answer be? Well, same as A times 3B over 1, because I just flip this over and multiply, which is the same as 3AB. What if I had A over B over 1/3? Then this is the same as A over B times this flipped over, 3/1, which is 3A over B. Make sense? Okay, the next question on the quiz had to do, let's solve this one. We have A over B over X over Y Z. I think you've seen the pattern. That's the same as A over B, it's on the top, times flipped over, YZ over X, which is A, Y, Z over BX. Okay. And actually, that's all the fraction stuff that I could think of that you really need to understand. This is a particular, I don't know, manipulation, shall we call it, that often get confused about, and I thought it'd be worth reminding. Alrighty, well, the next topic is algebra. That's kind of like algebra here in a way. It's resolving equivalencies. Algebra deals with equivalencies. We're going to look at problem 7, 7 and 8. If A equals B over C, then the question was, let's see, how can we resolve that into kind of equation where there's nothing on the bottom? How can we rearrange that? Well, if you'll recall, whenever you're dealing with an algebraic expression, an equation, the trick to simplifying the equation is to do the same thing to both sides. Just bring back recollections from years past, perhaps. If you do the same thing to both sides of an equation, it does not negate the equality. You can do anything to the two sides of an equation as long as you do the exact same thing to both sides and it doesn't affect the equality. I can multiply both sides of this equation by C, for example. AC equals B over C. I just multiplied both sides by C. When I do that, of course, I can simplify by C over C is 1, so that kind of gets rid of C altogether. And I end up with an equation that looks like this, AB equals C. That equation is the same as that equation right there. Or C, sorry. It is not the same as that equation over there. AC equals B is what I meant to write. Here's another one that is more like the kind of thing that you run into. If PV equals nRT, how can I rearrange that equation? Well, I could divide both sides by t, couldn't I? So that's the same as writing PV over t equals nRT over t. I divided both sides by t. I cancel those t's, and that's then equal to nr. Now at this point, you don't know what that equation means. You don't know what those variables stand for. It doesn't matter. The point is that you'll be able to move things around easily from one side of an equation to the other. By the same token, I could take this equation right here, and I could divide both sides by p. So I would end up with v equals nRT over p. I've divided both sides by p, and I get that equation there. Let's see. What if I wanted to solve this equation? That's a common math problem, right? Solve that equation for n. How would I do that? Well, that means I want n by itself on one side of the equation. Doesn't matter which. And I could do that by dividing both sides by what? Somebody tell me. RT. By RT. If I divide by RT on both sides, then I get PV over RT equals n. And the RT's cancel out on this side, leaving n all by itself. So we have n equals PV over RT. And let's see. I wanted also to do an example of substituting a variable. We did this in class. Let's do it example here. We talked about how energy of a photon is related to its frequency. Can anybody remember what the equation is for that? I bet you can, yeah.
E equals 1 over n squared.
Okay, that is,
Oh, that's a proportionality.
that's proportionality. We'll talk about proportionalities in a minute. And that is the relationship between the energy of an electron in its Bohr model compared to the orbit number. What I would like to know is for a single photon, what is the relationship between the energy of the photon and the frequency of the photon? This hand went up first.
E equals Planck's constant plus B or frequency. I mean, not plus, but times.
Good. E equals h nu. This is Planck's constant. This is the frequency. This is the energy. We also talked about the relationship between the frequency of a photon and its wavelength. Can anybody remind me of that equivalence?
Energy equals
Yes, sir?
frequency times wavelength.
Okay. I'm going to give you another chance at it.
C equals wavelength times frequency.
Good. Okay.
Sorry.
It's that C that we need to remember. What is C? Do you remember?
Speed of light.
Speed of light. The speed of light equals the wavelength times the frequency. Now, I can combine what I learned from two different equations by substituting a variable from one equation into the other. And we did that in class. I just want to be sure you understand how it works and why it works. First of all, I'm going to rearrange this equation. I'm going to solve this equation for nu frequency. How will I do that? I'll divide both sides by the wavelength. I want to get rid of that lambda there. Okay, so C lambda equals nu. Right? So far, so good. Now we can substitute for nu in this equation here, this side of that equation there. So E, instead of being equal to h nu, equals h times C over lambda. Or, as is commonly written, hc over lambda. And now the relationship between the energy of a photon and its wavelength rather than its frequency. Now we could do other funny things here, couldn't we? We could say, let's see, from this equation, what does nu equal? We solve that equation for nu, what does it equal? Yeah, it equals the energy over Planck's constant. And so we could now substitute that in here, couldn't we? We could say C equals, keep lambda, and for nu we substitute E over Planck's constant. You don't see this used very often. I guess it's not very useful. I don't know. But it's perfectly valid according to the equations and substituting the way we did. Any questions?
Can you do that again where you substitute one variable instead of each?
Okay. Did you follow this one here?
I got.
Okay. So we solved for nu and got C over lambda. Now nu appears in this equation. So I've rewritten this equation here. Okay. E equals h, so far the same. And now instead of writing nu, I've written this. Any other questions? Well, that's all I had for algebra. Our fifth topic today is proportionality. I want to reemphasize, as I've mentioned in class, that proportionalities are a way to show in a simple way, in a simplified way, how one thing relates to another. I'm going to make up a completely bogus equation, okay, with a whole bunch of bogus variables. We'll say G equals h mu lambda v w over RT squared. Now, you run into equations like this very often in science. And the typical reaction of anybody who's new to the equation is total panic. I mean, it's my reaction too. What the heck does that mean? What are all these things? How do these things work together? Well, the nice thing about proportionalities is it allows you to zero in on one part of the relationships that are shown in an equation like that and see it clearly. From this equation, if I keep all other things constant, but I allow t to vary, doesn't matter what t is, could be temperature, time, I don't care. If I allow t to vary, then I can say, I can interpret, I can read meaning into this equation by saying, I see from this equation that g varies inversely, not equals, but varies inversely as t squared. And that means that as t goes up, what happens to g? It goes down. In fact, it goes down really fast because t is squared. Okay? By the same token, let's say I wanted to know, well, how does g depend on v here? I kind of take on a myopic view of the equation and I say to myself, I'm going to ignore everything else. I'm just going to look at how g and v depend on one another. In other words, how does one vary with the other? G varies directly as v. And so if all other things are kept equal, none of these other things are changed, and I only change v, whatever g happens to be, as v goes up, g will go up. And that's how we can read meaning into something even that complex. And that's what's nice about proportionalities. The other nice thing about them is that if I know that g varies as v, then if I have two sets of conditions where I change just v from one set of conditions to another, then I can set up an equation, not a proportionality, but an equation like this: g2 over g1 equals v2 over v1. This is the v that corresponds to this g set of conditions. This is the v that corresponds to the g set of conditions. And if I know that I've doubled v from going from v1 to v2, then I know with a surety what has happened to g. If I've doubled v, what's happened to g? I've doubled it. If I triple v, I've tripled g. Okay? That's what's nice about this. I'll give you a more, if you're a practical kind of person, I'll give you this equation here, which we're going to deal with later. This equation relates for a gas, the pressure of the gas, the volume of the gas, the number of moles of gas particles, the temperature, and this is just a constant, okay? It's just a constant. You look at that and you say, oh my gosh, that's awfully complicated. But if you simplify it and look at just two variables, you can say this. The pressure of a gas, you tell me, how does it vary with the temperature of the gas? Varies directly. I can rewrite, I can interpret my equation as a proportionality by simply getting rid of all the other stuff and saying P varies as whatever's on this side, happens to be T. So as I double the temperature of a gas, what happens to its pressure? It doubles if all other things are kept constant. If I have the same number of moles and I have the same volume, then the pressure will double. Now I could rearrange this here, couldn't I? Get and solve for P, and I would get P equals nRT over V. You see that? That equation is the same as that equation. Now tell me, how does P vary with V if all other things are kept constant? Inversely. P varies inversely as V. Now that means that P2 over P1 equals, you tell me, V1 over V2. If now V1 is my starting conditions, V2 is my ending conditions. If I double the volume of a gas and keep everything else constant, temperature stays constant, number of moles of gas stays constant, R of course stays constant, it's a constant. One of the rules of chemistry is constants are always constant. Never forget that. If I double the volume of the gas, V2 is twice as big as V1, what will happen to the pressure? What will be P2 over P1? The final pressure over the initial pressure. I double the volume of the gas. V2 is twice as big as V1. What's the new pressure over the old pressure?
Small.
It's half as big or twice as small, however you want it, okay? It's half as big. And that's exactly what happens. The new pressure is half as big as the old pressure. Now, does that correspond to what you would think common sense would tell you would happen? If I take a volume of gas and I expand it so that it's twice as big as it was to start with, what do you expect the pressure, what do you expect to happen to the pressure? It goes down. And this is a way of saying that without invoking all these variables that complicate life for you. Yes?
Just as P varies with P, can V vary with P also?
Apparently, this says that the volume varies with the temperature. Now, let's think that through, common sense. I wonder if that's really true. If I raise the temperature of a gas and keep the pressure constant, what must happen to the volume? You ever done that? You get a gas hot. What happens to the if you keep the volume constant?
Expand.
The pressure increases, right? But if you allow the volume to change, then in fact the volume will go up as the temperature goes up. The volume has to go up as the temperature goes up in order to keep the pressure constant. Yes, sir.
With the constant, that's just for this formula, right? Like,
Which formula? Yeah, every equation has its own, maybe it has its own unique constant associated with it, or maybe not. Sometimes they don't have constants. Sometimes they do. The point is that when you go to the equation itself to the proportionality, you can just forget about the constant altogether. You're only looking at the relationship. Other questions? Yes, ma'am.
Why did you use, that's completely off topic, but why did you use the nuclear alpha?
Why do I use, oh, this isn't an alpha. Actually, that's a varies as sign in math. Okay? If I were to write an alpha, it would probably look more like this. Isn't that lovely? This is a varies as sign. It's like a fish, a Christian fish. I don't know. Any other questions? Yes. Yes, absolutely. Any other questions? Yes, ma'am.
Do all of the other variables have to be constant in order to create substitution?
No, but, well, constant in the sense that you hold them at value. Some may actually be constants. R is a constant in the strictest sense of the word. It never changes. It's a constant of nature. But if you hold these, we could hold these other variables constant temporarily for the purposes of looking at what this relationship is. This man has a
have to keep them constant
in order to look at just one of these relationships, you have to keep everything else constant. Yes.
Can you say PV is directly proportional to T if R stays constant?
Yes, that's correct. Yes, sir.
Why can't it be G1 over G2 is equal to V1 over V2? Or like just a directly
It
proportional?
could be. You can flip that whole thing over and it's still the same equation. G1 over G2 equals V1 over V2 is the same equation as the one that's...
But once you get a completely different answer?
No, you won't get a different answer. Try it. Just try. Write it down. Pick some numbers. Try it. And I guarantee if you do it right, you'll get the same answer either way.
Either way. Okay.
Either way. Because they're the same equation.
Okay, so because I've just noticed you always put the 2 on top first, but doesn't...
Well, it's because it's just a habit that I got into as a student.
Okay.
It just makes the math easier if you do it.
Okay.
Well, thanks for being here, folks. I hope that was helpful to you.